Linux Foundation Decentralized Trust Meetup. Today we have a presentation on privacy-preserving integration between Hyperledger Fabric and Substrate framework. So with that, why don't you take it away, Saeed?
Okay, hello everyone. My name is Saeed Muradi, and today I'm here to present my work to you called Privacy Preserving Integration between Hyperledger Fabric and Substrate Framework. So just to quickly start, I would just want to quickly go over the basic topics that that are related to this project, and I start by talking about what a blockchain is. So a blockchain is a digital ledger that is shared across a network of computer nodes, and it records the data via transaction creation and submit that data to a ledger. And as we all know, probably, a ledger is a type of database that is leveraged by blockchain systems. And it is a type of distributed database, which means that all participants can update the state of the blockchain. So because not one single entity owns the database, everyone can contribute to adding data to the database of the blockchain, which ultimately will change or update the state of the blockchain. And transaction data is stored on a block, which is connected to the previous block using the hash value of its data. So in order to keep or store our data, transaction data in a blockchain, we are having multiple components that are called blocks in a blockchain. And these blocks are connected to each other using the hash value of their data. And I will explain what I'm talking about in the next slide. And the participating nodes reach a consensus about the validity of the transactions using the blockchain's consensus mechanism. So because, as we all know, a blockchain, at least when it started to become a thing, it is started by being something decentralized, which means that there's no centralized entity governing the system. Because of that, there should be some way to validate the transactions. And to do so, we introduce something called blockchain consensus mechanism, which is the mechanism or like the policy of the nodes to validate a transaction in the blockchain. And to just quickly talk about the blockchain diagram, let's say we have a block called block one, this is the first block of the blockchain, which consists or hosts multiple transactions. And this block is connected to the second block, which also stores multiple transactions. And the second block is also connected to the third block. And for this connection to happen, we have the hash value of the first block, for example. As I said, the first block is the originating block, so there is no previous hash because that's the first block. And the second block stores the hash value of the first block and the block itself. So the second block, if it wants to connect to the first block, it should also preserve or store the hash value of the previous block, which is the first block in this case. And likewise, the third block is also connected to the second block by storing the hash value of the second block. This will prevent data tampering, because if someone wants to tamper a block in a blockchain, they should also change the previous block. And for changing the previous block, they also have to change the previous block of that previous block, which makes it extremely difficult for someone to tamper the data in a blockchain, because if they change the data, they have the hash value of it also changes, which will be incompatible with the previous blocks of that blockchain, of the block that it is tampered. And because this is related to the scope of my project, I am going to talk about what blockchain interoperability is. Blockchain interoperability is the ability of different blockchain networks to securely communicate with each other exchange data or assets, or participate in each other's consensus. So as we know, there are multiple blockchain platforms that are used for different use cases, and they have different applications. And these blockchains are usually isolated from other platforms, so they cannot communicate with other blockchain platforms. And addressing this problem will be something that we call the blockchain interoperability, because this will enable the communication to happen. And this communication can be in different ways, as I said, exchanging data or assets, or participating in their consensus, or communicating with each other just in general, just talking to each other. And an example use case for this one is digital cryptocurrencies, like let's say Bitcoin and Ethereum. These are two very well-known cryptocurrencies that we know about. And these two, each of them, they have their own protocol and consensus mechanism on token standards. So they are operated on very different systems. And because of this incompatibility, a Bitcoin user cannot transfer assets to an Ethereum user, or vice versa. And interoperability solutions enable this communication. So by providing interoperability, a Bitcoin user can transfer asset to an Ethereum user, or vice versa. And when it comes to blockchains, there are different types of blockchain networks. And if we want to talk about how we categorize blockchain networks, there are different ways that we can do the categorization. But one of the most famous and commonly used ways of categorizing blockchain networks is by categorizing them based on their availability to the public users. And having said that, blockchain networks are usually classified into two major groups. And the first one is the public or permissionless blockchains, um, which is the type of blockchain that anyone can access to, add data to, or participate in its consensus. So basically, if you are having a public blockchain, such as Bitcoin, Ethereum, all the cryptocurrencies that you know, and many others, these are considered public blockchains because everyone can access to the data of these blockchains. They can see the activities of other people. They can join without anyone authorizing or authenticating them. Or they can also participate in the consensus, like if a node can join in to the Bitcoin network and participate in the consensus. On the other hand, we have private or permission blockchains, which is a type of blockchain that restricts access to authorized users. So not anyone, unlike the public blockchains, not anyone can access private blockchains, and participants may not have the permit to add data or participate in the consensus. So based on the blockchain policy and guidelines, there might be restrictions applied or imposed on people who want to be part of the blockchain system. And their activities also monitored, and not any some different people might have different access level to blockchain components in the private blockchain system. And because Hyperledger Fabric is one of the technologies that I use in this project, I'm going to quickly talk about what Hyperledger Fabric is. Hyperledger Fabric is a type of permission blockchain framework that is open source, modular, and is primarily used for enterprise use cases. And sorry, it allows developers to build permission blockchain applications with high levels of confidentiality, scalability, and flexibility. And it is part of the Linux Foundation's Hyperledger project. And here we have the transaction flow, the Hyperledger Fabric. So when a client wants to submit a transaction, they definitely have to have the Fabric SDK because they should have the Hyperledger Fabric installed on their end. And using that, they will, when they attempt to make a transaction and submit it to the Hyperledger Fabric framework, they will send a transaction, something called transaction proposal, to the endorser node. And the endorser node is a component in Hyperledger Fabric, which is responsible for endorsing and validating the type of the or the structure of the transaction, who is sending it, and how they are sending it, all the things, all the policies that the transaction should align to are being checked by the endorser node. And after the endorsement, the transaction response will be sent back to the client. And after that, the transaction response will be the proposal will be sent to the order node, which is a component for ordering the transactions and for submitting them later to the committer node. And also, like the order node sends a notification to the endorser node saying that like this is a transaction that I received. And order node also validates the structure of the transaction proposal to see it is a valid, verified structure for the proposal. And after that, the order node will send the transaction proposal in order to with order to committer node, which is the final node that is going to finalize the transaction, and it will submit the transaction or append it to the vault state. And committer node also, just like order node, will validate and verify everything and make sure that like everything is aligned with the policy of the Hyperledger Fabric. And just like Hyperledger Fabric, this is another platform that I use for this project. So I'm going to quickly go over the basics of this platform. Substrate is an open source blockchain development framework that can be customized to create both public and private blockchains. And it is built using Rust language, which is well known for its performance and security. And it is developed and currently maintained by Parity Technologies. And the diagram of a substrate-based network can be broken down into these components. If you have a substrate node, for example, there are multiple components that you have in your network, which can be categorized into client, application logic, and runtime. And the client is the part where you store all your configuration, all the palettes, what we call something that we call palettes in Rust. You are responsible for managing all the configuration files, all the modules and libraries that you are using or leveraging for your project. And these 6 palettes that I just mentioned here are the necessary ones that are in every substrate node that you see out there: networking, storage, RPC, consensus, transaction, and telemetry. And beside that, in each substrate node, you have the application logic and state, which is WebAssembly or WASM. WASM is basically a binary instruction format that you use for running your code on different platforms, especially browsers. It's like a very effective way because it also provides security, privacy, and it is highly scalable. The performance is really good. So this is like something that is used by Substrate node. And to submit your request and to actually give your commands to the WebAssembly state, you need to have your runtime call executor, which is the component that is responsible for calling the functions and methods that you need that you defined in your substrate node to run your node and do all the necessary actions that you define for your substrate. So runtime call executor will be the component that is sending all the requests for taking any actions, and it will be translated to a WebAssembly format, and this will later on will be operated inside your substrate node. So after talking about the necessary information in my project, I just want to talk about what do we do in this project. So we propose a solution to connect Hyperledger Fabric to Substrate framework, and we also introduce mechanisms to preserve the user's data privacy. And finally, we evaluate the performance of each approach and compare them to see which one is faster. So before we get into this, I just want to quickly talk about the related works that are close to what we did in this project. So there has been numerous attempts to propose a universal solution for blockchain interoperability. And like, I cannot talk about all of them because that takes a lot of time, but some of the most famous ones are Hyperledger Cacti, Polkadot, and Cosmos. Hyperledger Cacti is a blockchain interoperability framework developed by the Hyperledger Foundation, which provides tools, APIs, and protocols for enabling integration and interoperability among heterogeneous blockchains, which means blockchains that are not compatible with each other necessarily. And these blockchains can be permissioned or permissionless. And it leverages cryptographical techniques such as zero-knowledge proof to secure communication and prevent data tampering. However, Hyperledger Cacti is a quite complicated structure or framework to enable interoperability. So it is complicated to develop, which also will be cost inefficient for many smaller businesses that cannot afford the cost of development. And also, it is the performance overhead can be high because the transaction proof and all the cryptographical techniques, they may be good for enhancing the security, but on the other hand, they damage the performance of the system. The next famous interoperability solution that I know is Polkadot. And Polkadot is a multi-chain blockchain platform designed to enable interoperability, scalability, and security for blockchain networks. And it incorporates relay chains, which acts as the central hub for connecting multiple blockchains. And the multiple blockchains in the context of Polkadot are called parachains. And it is quite a scalable, customizable, and enable forkless upgrade. So for upgrading, you don't need to fork from the original state of your blockchain and do all the changes in the fork version of your blockchain. You don't need to do any forking, and you can upgrade everything on the blockchain state itself. But the problem is Polkadot system also has some problems. The first, it is complex to develop, and it also limits the number of parachain slots. So you cannot add as many parachains as you want to the Polkadot system. And also the governance model for managing all the parachains that are connected to the Polkadot engine is quite complicated. And finally, this is Cosmos, which is the very famous interoperability solution. Cosmos enables communication and transactions between blockchains using its IBC protocol, which makes it a true multi-chain ecosystem. And it uses Tendermint Core, which is a powerful consensus engine for transaction validation, which is basically the same as consensus mechanism. Cosmos achieves a scalability through horizontal scaling where multiple independent blockchains, or called or zones in the context of Cosmos, operate in parallel and connect to a central hub. So basically, in Cosmos, you have something called Cosmos Hub, which is the component that is going to interconnect every other blockchain network to itself. So if one blockchain wants to communicate with another blockchain, they should use the Cosmos Hub as their intermediary component. However, just like other solutions, Cosmos has some downsides. The first thing is it is not perfectly scalable. And also it lacks a single universal security model. So because Cosmos does not provide any security mechanism to protect the privacy of its users, so each blockchain network should propose their own security model, which will complicate maintenance of the entire system. And it can be also incompatible because one security model might not be compatible with another security model. So before we get into the architecture, I just want to talk about the reason why we need to connect Hyperledger Fabric to Substrate. So there might be different reasons. There are different incentives. For example, private blockchains such as Hyperledger Fabric may like to share part of their data with external entities. So for example, let's say you have a supply chain management system on Hyperledger Fabric, which is storing some data about your supply chain system. And after a while, you have some data that you're not going to use anymore. Or the privacy of your data is not something that you want to preserve anymore, let's say. So in such case, you may like to expose your data to the outside world for let's say for benefiting from it, or just like letting other people access it so they can like analyze it, or just basically opening up your doors to communicate with the outside world. The second reason can be the fact that Hyperledger Fabric specifically might want to connect to the global market. So in my example, in the supply chain example, if they ever wanted to connect to the global market, if they continue being a permissioned blockchain and stay isolated from the outside world, they can never connect to the global market. However, if they open up a gateway or a way for other components, external entities, to access their data, they will be able to connect to the global market. And they can also take advantage of high computational power of public blockchains to enhance their security. So for example, for consensus mechanisms, for security measurement policies that we have, or for any other policy that you want to apply for our permission blockchain, we can connect to the public blockchain. Or for example, for restoring their chain of hash values in a public network, Hyperledger Fabric might be interested in connecting to a public blockchain. Okay, and now I'm going to talk about the architecture that we are proposing. So in one end, we have the Hyperledger Fabric with something called interoperability chain code. So we have a smart contract or chain code installed on our Hyperledger Fabric node. And we also have the Fabric CA, or Hyperledger Fabric Certificate Authority, next to it. And on the other side, we have the Substrate node or Substrate network, which also has an interoperability chain code. And in the middle, to enable this communication, we have something called certified relay services. So the relay service is comprised of 10, or at least 10 servers or relay services that are responsible for passing or forwarding the requests from Hyperledger Fabric to Substrate or vice versa. And this request sending or transaction forwarding is done by using the interoperability chain codes. So if a Hyperledger Fabric user wants to submit a transaction to a Substrate user, they should have an interoperability chain code that is going to connect to these certified relay services. And these certified relay services, in some ways that I'm going to talk about later on shortly, are going to connect to are going to send this request to the Substrate node, which is going to handle this transaction using its own interoperability chain code. And the same thing happens when a Substrate user is going to initiate a transaction against Hyperledger Fabric. So I just went on talking about the overall abstract architecture of my my project. So now I'm going to talk about the transaction flow that happens in this architecture. So let's say you have a user called Bob. On one end, it could be Hyperledger Fabric or Substrate, doesn't matter. And you have Alice in the other end, and you want to submit a transaction from Bob to Alice. So Bob will first send its request to the Substrate or Fabric node, which ultimately will send the request to the smart contract that is installed on that specific network. And this request will be encrypted and sent to the first relay service that you have. And this relay service will decrypt the service, will decrypt the request or part of the request, I have to say more specifically, and will encrypt and sign the request again. And it will send it to the second one, the second relay service. And the second relay service will do the exact same thing as the first relay service. And it will also encrypt and sign the request. And it will send it to the third one. And this will happen several times until the last one, the last node or relay service that we have is going to sign the request and hand it into the smart contract that we have on the other side. And that smart contract is going to process a transaction and hand in the request to hand in the money or the asset or the data, whatever that is, to the other user on the other side. And there are some notes, there are some things that I have to talk about related to my architecture. The relay service information is stored on the interoperability chain code. So there might be questions about how these smart contracts that we have on a Hyperledger Fabric or Substrate know about the relay service. Well, their configuration, their IP, their address, their signature, their encryption data, everything about them is stored on the interoperability chain code. So we have them all in both of our networks. And the interoperability chain codes manage relay memberships and monitor their performance, activity, and livability. So to make sure that the relay services are acting and behaving as expected, interoperability chain codes always manage the relay memberships and monitor their performance by sending them just dummy requests, like ping requests, and also managing their activities. And someone might say, okay, who is going to do this? Who is going to tell the interoperability chain codes to do this? Well, we have some users in Hyperledger Fabric, because Hyperledger Fabric is a permission blockchain. they can have this either on an interoperability chain, on a different chain code that is going to manage the membership or the performance of the relay services or their activities. So if they went down, for example, if they shut down, then the interoperability chain code will not send any request to that unavailable relay service, for example. And also their livability, as I said, if they are not live anymore or their performance is not high enough or is not satisfactory, then the interoperability chain code will not send any request to that relay service anymore. And any new relay service should be authorized by Hyperledger Fabric CA or any other certificate authority before joining the network. So this is to make sure that not everyone can join the relay service that we have, and everyone who is going to participate in our relay service should be certified either by the Fabric CA or by any other certificate authority that we have, to make sure that no one is going to steal our data, tamper our data, or damage or manipulate the process of interoperability that we have between these two networks. And lastly, the user identity is hidden throughout the process. So the very important thing about the architecture is that throughout the process of forwarding the message to different relay services, none of the relay services actually know who the user is and who is sending this message. This is to ensure that no one is going to monitor the activity of a user, especially the Hyperledger user, because, for example, a Substrate user doesn't matter if their activity is being monitored because they are participating in a public blockchain. But from the Hyperledger side, it matters because it's a permission blockchain. So we should protect the privacy of our users by providing some privacy mechanisms or hiding their identity from third parties like the relay service. And the advantages of our architecture is as follows. The relays are blockchain agnostic, which simplifies development and maintenance. And which means that the relays, if you want to deploy a new relay, you don't need to think about what you're going to do with Substrate or Fabric, in the sense that everyone should be able to, as long as they decided to participate in this interoperability, they should be able to access the relays regardless. So in that case, these smart contracts that we deploy on both ends should not worry about the compatibility or the ability of the relays to respond to them. So there are no relays that only serve Substrate or only serve Fabric. All the relays are blockchain agnostic, and they serve everyone who is going to access them. And neither the Hyperledger Fabric nor the Substrate framework are employing any additional entities to enable interoperability, making our solution generic and applicable to most blockchain systems. So the point that is important about this architecture is that there are no components that you are using beyond the scope of a Hyperledger Fabric or Substrate framework itself. And as a result, this will make our solution generic, and it makes it applicable to most blockchain systems, because we are not having any extra assumptions to enable this connection. And also, the relay services are verified by Fabric CA, which ensures that the data is handed into to trusted entities. This is something that I just talked about in the previous slide. And but there are some things that still look ambiguous in the architecture. So how do the relay services forward the transaction data? It's just basically, because I just showed some forwarding in the process of sending the transaction from one end to the other, but I didn't talk about the mechanisms or the policies through which I am gonna send this data from one end to the other. Well, we decided to leverage some techniques to make this happen. So we incorporated source obfuscations protocols for transaction forwarding. So what we do is that we are not just forwarding the transaction for no reason, because that will just delay the transaction delivery to the other end, and it will just damage the performance of our system in general. So there are some reasons that we are doing so, and the main reason is we want to obfuscate or hide the origin of the transaction. And this is because it prevents the origin of the transaction to be compromised. So we don't want to, for example, an adversary or an outsider to know who is sending this transaction. For example, let's say someone tampers or have unauthorized access to one of the relay services that we have. In some way, they have their hands on the data or the activity of that relay service. We want to make sure that by just monitoring their activity, they cannot know about the origin of the transaction. Is it Substrate? Is it Hyperledger Fabric? Is it any other network? So we just want to complicate the process of transaction, transaction forwarding for the user, for any malicious user, so they cannot know anything about the origin of the transaction. This is because also there was some problems related to Bitcoin, for example, which enabled to loss of millions of dollars and assets from Bitcoin for users, because someone could track the origin of their transactions, and in some way they could have access to their asset, which was something that damaged a lot of users in Bitcoin, as a prime example. And the protocols that we use for this source obfuscation thing are Dandelion and Clover. And to just quickly talk about the incentives behind obscuring the transaction origin again, I have to say that Hyperledger Fabric is a permission blockchain, and the relay service as a third party should not know anything about the origin of the transaction. So as I said, the other side doesn't matter that much, because Substrate in and of itself is a public blockchain. It is a framework that can be deployed, that can be implemented both ways. So it can be public and private. But it is usually used as a public blockchain, and in our architecture, we are assuming that Substrate is a public blockchain. But on the other end of our communication, Hyperledger Fabric is always, all the time, a permission blockchain, and a permission blockchain should protect the privacy of their users. So a relay service that is an outsider, even though they are certified by Fabric CA, they are still an outsider, and they should not know anything about the origin of the transactions. And intermediary components such as relays and bridges are usually prone to data tampering, eavesdropping, and de-anonymization attacks. So enhancing their security will improve trust across the blockchain system. So as we all know, there has been numerous security attacks against blockchain systems, especially when they are taking advantage of bridges and relays to interconnect themselves to other platforms. So because of that, and because we want to protect our data to enhance the security and privacy of data and prevent data tampering and eavesdropping and the anonymization attack, we have to propose some solutions that are going to enhance the security. So the first approach that we use is Dandelion++, which is a protocol that protects cryptocurrency transactions against the anonymization attacks during transaction propagation. So Dandelion++ is a protocol that is originally used especially in Bitcoin and Ethereum, and it protects the cryptocurrency transactions, especially against the de-anonymization attacks. So it will make it very difficult for an adversary to track the origin of a transaction. And it provides an opportunity to aggregate transactions before broadcasting them to the entire network. So Dandelion++ is a protocol that first makes sure that the transaction is aggregated and it is sent to enough nodes. And after that, it has then another phase that is going to broadcast the transaction to the entire network. And it consists of two phases. Dandelion++ is operated in two phases. The first phase is a stem phase, and the other one is the fluff phase. And just quickly going over the diagram of Dandelion++, I can say if Alice wants to send something to Bob, they first will send their transaction or their data to the nodes that we have. And these nodes are going to forward the transaction data or just the transaction to each other randomly couple of times or like several times. And after the stem phase is done, we have the fluff phase where we have again we have some nodes or relay services that are going to receive the transaction data. They all have to receive the transaction data, and finally they will all send the transaction to Bob. The second approach that we use in our project is Clover. And Clover, just like Dandelion, is de-anonymization is a protocol to prevent de-anonymization attacks. And this protocol is originally designed for Bitcoin peer-to-peer networks. And it protects the source of transaction messages by obscuring the sender's identity through the relay system. And it comprises of two phases. Just like Dandelion, we have two phases in Clover. The first one is the proxy phase, and the first one is the proxy phase, and the second one is the diffusion phase. And just going over the diagram of the Clover, I can say, just like the Dandelion example, if Alice is a user in Substrate or Hyperledger that wants to make a transaction to Bob on the other side, they first have to go to a phase called the diffusion phase. And I think this is reversed, yeah. And then in the diffusion phase, there will be multiple nodes that are going to forward the message to the next node or relay service that we have. And after this step is done, the transactions are all sent to the proxy phase. And all the nodes are going to receive the transaction data. And then finally, the transaction will be delivered to Bob. And to just quickly have a demonstration of my work, I am going to show you Dandelion, for example. I am having 10 servers that I'm running on my computer, and I am running some requests that are being sent to these servers using the Dandelion++ approach. And these requests, as you can see, the path is the path is there. The path is actually showing what servers or what relay services are receiving the request in order. So the 3006 is the first server that is receiving the first request, for example, and and 3006 is forwarding the message to the 3008. And just like that, the second one is 3006 and 3004. And these are random requests that are generated from substrate to fabric or fabric to substrate. It can be both ways. And also, the transaction proof is generated and is sent back to the relays because the transactions should be verified. And if we see the result, as you can see, there are transactions that are sending or forwarding the request to more than 2 relay services. So in this case, for example, we are having 5 servers that are receiving the request. And if we just quickly see the request logs, as you can see, we have the request ID, we have the ID, we have the network, we have the number of forwardings and total forwarding time. So if you see like the network is something that is randomly chosen for the request generation, and the number of forwardings is indicating how many servers are receiving the request, and the total forwarding time is the total time that takes for each request to reach its destination. And if you just like quickly want to check the server code, here is the server code that I implemented. So we are having functions, methods for invoking substrate and fabric network. We are having functions to invoke the code locally. We are having functions for encrypting and decrypting the message, and also signing the requests. So these are all the features of the code. So finally, if we want to evaluate our architecture, we decided to do the evaluation in the following way. The evaluation is done based on the performance of each approach, and it measures how much time each approach takes to process a transaction. So what we did was we tried to send 2,000 transactions for each approach randomly from one side to the other. And we averaged out their response time, and we try to compare the average time of each approach. And the transaction invocation time is excluded from the total time, because also the invocation of a smart contract takes some time. So we excluded that time from the time that we are just forwarding the message request. The source obfuscation approaches are compared with another approach called fastest ping approach. And just quickly talking about what is the fastest ping approach. It forwards the transaction merely because based on the availability of the relay. So if if a relay is responding pretty quickly, the transaction will be sent to that specific relay. And each relay sends a ping request to all the other relays to see which one responds faster. So every time a relay will send a ping request to all the other relays to see which one responds faster than the one with the fastest response time will be selected as the forwarding destination. So one relay will send the ping request to all the other relays, and the ones with the fastest response will be the one that is going to receive the transaction. And forwarding will be repeated at a random number of times. And to just show the evaluation diagram, here we have the three approach that I just talked about. We have Clover, Dandelion++, and shortest ping plus random forwarding. And as you can see here, in for example, in Dandelion++, the number of forwardings. Okay, so I just have to talk about this. On the x-axis, we have the number of forwardings, and on the y-axis, we have the average forwarding time that I talked about. So as you can see here, the Dandelion approach will significantly increase the forwarding time overhead after a certain amount of time that you forward the transaction. So if you forward it more than 9 times, 10 times, for example, it will just skyrocket the transaction forwarding time. However, on the other hand, Clover could maintain a good balance between the number of forwardings and the number of and the average forwarding time. And the shortest ping or the fastest ping, as I talked about, is also having a steady forwarding time. As you can see, there is not much change based on the number of forwardings that you do. And the takeaways of the diagram or the evaluation diagram that I just showed is that obviously the fastest ping approach will have the shortest processing time because that will be the only requirement that the fastest ping approach has. There's no transaction source obfuscation or anything like that. Just sending the message as quickly as possible. So that's why the fastest ping approach is the most reliable one. And the number of times that Clover forwards a transaction does not exceed the number of available relays. So that means that in the Clover approach, the number of times that the transaction is forwarded is actually controlled and is limited compared to the Dandelion plus approach, because Dandelion plus can have the transaction forwarded as many times as possible, especially in the first phase, the stem phase. So it may not be the best choice to have Dandelion implemented for your network if you are also trying to maintain the performance. And Clover's processing time remains steady, while for Dandelion++, we experience a significant rise if we forward a transaction more than a certain number of times. So as I showed in the diagram, after a certain amount of times that you forward the transaction, because there are also other transactions that are being parallelly processed by the relay service. Just this mass forwarding of the transaction will significantly damage the performance of the system. So that's why Dandelion++, Clover is outperforming Dandelion++. Okay, I am done with my presentation. Thank you for listening. If you have any questions, I will be happy to answer.
Yeah, if there are questions, feel free to type in the Zoom chat or just come off mute or use the raise hand feature. And I'll check on
Oh,
YouTube to see if there's questions there.
okay, sure.
Hey guys, do you hear me?
Yeah.
So sorry, I just jumped. Actually, the last 30 minutes was really insightful, and thank you so much. My question is really like simple. So now we got the blockchain, and I can like understand the general idea of like having a chain and like approvals and all this encryption. Can you please explain to me what makes the Hyperledger difference than the other type or revolution? Sorry if you mentioned anything about this at the beginning because I missed the first 30 minutes. I'm just a little confused based on like Hyperledger and its use case and other type of tools that are similar. Thank you.
Yeah. Okay. Yeah. Sure. Thank you for your question. So, Hyperledger Fabric is a permissioned blockchain, as I talked about. It is something that is developed for users or for enterprises that are going to implement a blockchain system for their own use cases, because it is not something that is going to be publicly available. And as a result, it is something that other blockchain networks cannot have access to, and this will make Hyperledger Fabric an isolated network. So this is the reason why connecting Hyperledger Fabric to other blockchain networks will be something of interest to some people, because this will enable other users to have access to Hyperledger Fabric in case that enterprise is willing to be connected to the outside world. And like if you're talking about the features of Hyperledger Fabric, I can say it is customizable, is easily maintainable, and it has a huge foundation of developers behind it. So it is getting constantly upgraded and updated. So that's why it is something that is reliable, and it is a cutting edge technology, because it is getting constantly maintained by the Hyperledger Foundation and Hyperledger Labs. So yeah, I guess those are the features of Hyperledger Fabric, if I answered your question.
Yeah, definitely. Thank you so much. I will
You're
try to
welcome.
look up your name if you're available on LinkedIn side.
Okay, sure. Thank you. There are many profiles of my name, so I
You can
I
send the
hope
link if you want to.
yeah, I will send the link in the chat. Sure.
Thanks a lot.
You're welcome. Okay, I'm seeing a question in the chat. Can I respond to it? Is it okay?
Yeah, please.
Yeah. So how can one subscribe to this service? So okay, and this is a good question. So if a Hyperledger Fabric user wants to subscribe to this platform, they don't need to do anything necessarily with the relay service. Relay service is something that is going to be uh, provided by an outsider or like external entity. But if you're talking about the relay services itself, as I said, the only requirement is that it should be aligned with the policies and the guidelines of Hyperledger Fabric, because that's the only permissioned party that we have in this communication. So as long as they have the certificate of Fabric, Hyperledger Fabric, there is nothing else that they need to do. And yeah, that's pretty much it. You're welcome. I just sent my LinkedIn on the chat, by the way. If like
And I can share that LinkedIn. So after this, I'll send an email out to everyone who signed up with the video recording and your LinkedIn. So if people have questions, they can reach out.
okay, good. Thanks.
Any other questions from anybody else? Looks like not for now, and I didn't see any additional questions on YouTube. Like I said, I will send your LinkedIn account or your LinkedIn profile out to everybody. So if anybody else has additional questions after this, feel free to reach out. And with that, thank you, Saeed, for presenting, and thank you everybody else for joining.
Thank you so much for your time and for the opportunity. I appreciate that.
Of course. Yeah. Thank you for sharing what you've been working on. All right. Well, thanks everyone. We'll talk to you later. Bye.